A lot of the things we're doing in this course are estimating our values because we're trying to see what is the truth about the population, not just our sample. So it all depends on how you organize your data, how you collect the data, how you analyze data, and what methods you use to process the data. Here we have in this section, this next two sections, we're going to be using the charts in the book. I don't know if I gave it to you guys in your packet or not, but we're used to the Z chart already, the Z-score table. That new one I gave you hopefully has tables in the back of it. See if it has the T chart back there. It should. The last three pages, yes. The last 3 pages of the thing. There we go, yeah. No, yes, that's the one. Yes, because now depending on how big of a sample you need or you have, that will dictate which chart you use and how accurate you're going to become. And we also have a bunch of other terms we have to define. Point estimate, confidence interval, how to determine the sample size. How big of a sample size do we need to have a valid test? All this stuff, that's what we're talking about the next two sections. And everything we talk about is trying to predict what's happening in the population. All right. So in this section, estimating a population proportion, let's first define a few terms. Point estimate. The sample proportion denoted by P hat. Is the best estimate or single value estimate. We'll talk about these in a second. Of the population proportion. P. So P hat is the sample proportion, and P represents the population proportion. So again, that's the point estimate. It's the best estimate that we have. The next term we're looking at is confidence interval. Just by the word confidence interval, you can pretty much guess what it means. We can use a sample proportion to create a confidence interval we can use a sample proportion to create a confidence interval estimate of the true value of a population proportion P. And we need to know, we should know how to make or how to create and interpret that confidence interval. So what do you think, in your own words, what do you think confidence interval would mean? Interval of what? And why confidence? I mean, what does confidence mean? What are we trying to do with all this stuff? We have a sample. We're trying to do what with the sample? We're trying to estimate the population values. So what a confidence interval is we're going to create an interval where we are a certain percent certain that the population value will be within that interval. So if I said, pretty much if I said, I'm thinking of a number between 1 and 100, and I'm confident that you guys will think it's between 45 and 50. So that's my confidence interval, is between those numbers. And then we'll take a survey and see how far everybody thinks. So that's what this is all about, to see how sure are you of what you're saying the answer is. And all of these are calculated with formulas. Sample size. We need to know the sample size needed to estimate a population proportion. Why is the sample size important? When you hear those advertisements on TV that says 75% of the dentists prefer Colgate than any other toothpaste. Do you believe that? If not, why? If so, why? Or does that influence you one way or the other? If 75% of the dentists surveyed prefer Colgate, is that going to make you think about, hey, what toothpaste should I get? Or what exactly is the factor that makes you decide what toothpaste to get? You'd be surprised what the answer usually comes out to be. It's what my mom and dad used growing up. Very few times do people ever change stuff that they grew up with. They're comfortable with it. Even though when it comes to toothpaste, there's no difference. As long as it has fluoride in it, it's toothpaste. It's all the same. It's just the only thing that changes is the package and the price. You can make it yourself. Just go out to the chemistry store, get some fluoride, and mix it up with baking soda. And you have this just the same quality as toothpaste. But the size of the sample is important because obviously the bigger the sample, the more accurate the estimation. But the bigger the sample, the more expensive, the more time consuming it is. So there's an optimal number of samples that we need, depending on the population, that will determine whether we have a good chance at getting an answer correctly. Here's notation that we'll be using here. X is what we're looking for. We're looking for the probability of some outcome. So this is the number of successes. Notice it's in quotes because success is not always a good thing. Because what if you're studying the number of car accidents at an intersection near bars? Well, what's a success for your study? A collision. So that's not always a good thing. The N is always going to be your sample size. That's small n. Capital N is your population. P is the population proportion. That's what we're looking for. And it's defined as N or X over N. Your successes over your sample size. P hat is the sample proportion. X over, this is a capital N, I'm sorry. This is a population. So these are the symbols we'll be using in this section. Note. The point estimate is used to get the best proportion of the sample. And then as of the population. We use the point estimate of P it is unbiased. Hence, most consistent of the estimators. What's that? So hence, this point estimate is the most consistent of all the estimators. Because we have multiple estimators that we can use. It's just the point estimate that we will define. That's what we always use. Let's look at an example here. Okay. In a Sallie Mae survey of 950 undergraduates, and 53% of them said they take online courses. Based on that result, find the best point estimate of the proportion of all undergraduates taking online courses. So we have to define is what is P? Because we're looking for the population proportion. So what is the value of P with what information is given? Nope, that's the size. Is what? What would be in decimal? Right. So 0.53. Because what that says is 53% of whatever the number of samples undergraduates there are. Then we're gonna talk about how confident we are about this. We'll look at 90, 95%, 98% confidence intervals and see what that means. Why do we need confidence interval? It has to do with the word confidence. Because if I give you a confidence interval, then I am confident. There's a certain reasoning, there's a certain validity behind that. It makes it a much better estimate. It's more than just a good, it's a much better estimate. I don't want to say exact, but what we're saying is we're trying to estimate where the population is going to be. And if I give you a confidence interval of certain numbers, then I'm saying that I'm that confident that the population is going to fall inside there. So the confidence, what that really tells us is the confidence interval is a range of numbers, or as it says, an interval of values that are used to estimate the true value of a population parameter. It's a range, it's an interval of numbers that we're saying that we are this confident that the population values are within this range, this interval. How do we find confidence intervals? Just abbreviate confidence interval CI. It makes it much easier to write that way. The confidence level and critical values to find the confidence level, we have to have a confidence level and a critical value are defined. The margin of error is known. So with confidence interval, we can now determine, well, we can determine which one of the level of confidence and the critical values that are being used. And then from there, we can find a margin of error. Have you ever heard of margin of error before? What is a margin of error, do you think? And this is why statistics really isn't considered by pure mathematicians as a math course. Because mathematics, if x plus 3 equals 5, what does x equal? 2. Can it be anything else? No. Statistics, on the other hand, if I'm saying that the answer is 2, so if the answer is 2, I can go plus or minus 1. This is the margin of error. I can notice if I have 2, I can either be above it by 1 or below it by 1. So it gives you an error estimate. An error estimate, it's already there. I'm saying I could be wrong. If I'm wrong, I'm within this much area. So it's not exact. It's an estimate. Statistics and probabilities are nothing but estimates. Now, instead of using confidence level, we always sometimes use degree of confidence or the confidence coefficient. Those are synonymous words that tell us, okay, this is what it could mean. But all these words are the same thing. They mean exactly the same thing. Level. Here we have most common confidence levels. I could be 90% confident, 95% confident, 99%, or was it 98% and 99%? But these are the most common ones used. So this would be written as 0.90, 0.95, 0.98, 0.99. These correspond to an alpha. Oops. That's your confidence level, an interval. So if my confidence level is 90%, my alpha is 10% or 0.10. If my confidence level is 95%, what's my alpha? 5% or 0.05. And to be honest, this is the most commonly used one here, 95% confidence interval. At 98%, what's my alpha? 2% or 0.02. And at 99%, it's 1% or 0.01. Okay, all this stuff is looking great. But what does the alpha tell us? Where is that in the whole scheme of things? Let's define a couple words. Critical value. Critical value is a z-score on the borderline that separates the z-scores that are significantly low or significantly high. Remember when we talk about significantly low, significantly high, what picture do we use? Yeah, we look at a normal curve. And then we have those two lines there. And typically, those two lines are plus or minus 2 standard deviations from the mean. If a number is in here, it's what? Significantly high. If a number is in here, it's significantly low. If it's between there, it's nothing. Well, this area here and this area here That's what alpha defines. So this part is alpha over 2, and this part is alpha over 2. And the critical value is the z-score at that alpha. Because why do we need the z-score? What does it do for us? Remember, the z-score is this part here. That's that line. It's separate. It tells us what, if I'm looking for this area here, once I find the z value, it tells me all this area down here. I subtract it from 1, I get this area. So this is 1 minus the z-score is my area inside here. If I'm down here on the left side, then whatever my z value is. Because why? Because the z chart tells us to the left of the number. When I get your z charts out also will be, because we need to start looking at these values. Here, there it is. Okay, for example, let's look at my confidence level is 95% confident. I'm 95% confident that the population proportion will be within my interval. So what alpha is that? 5%. So this is 0.95. This is 0.05. Because we're looking at, okay, this is what's called a two-tailed test. These are called tails. This is the right tail, and that's the left tail. That's why it's called a two-tailed test. So when we have a two-tailed test, we have to take our alpha and divide it by 2. So 5% divided by 2 is 2.5%, which is 0.025. Remember, now what we're looking at here is this. So this is my alpha over 2, my z-score of that one. I have to find the z value. So I know my alpha is going to be this. How do I find the area for it? So if this is 0.025, what's this whole area? 1 minus 0.025, which makes it 0.975. What do we use this for? Now, what does this tell us? This is the area. the area to the left of this line. We're trying to find the z-value. We know the area. How do we find the z-value? Look in our chart. Look for the number that comes closest to 0.975 inside the chart. Oh, there it is. No, that's 0.9975. I want 0.975. 9750 right there. Oh, I lost it. 975. So what's my z-value? I go to this side. It's 1.9. And then I go up 6. So my z-value is 1.96. Now I know the z-value. I know the area that's going to take in there. Because now I could use my, remember, some of the formulas have z-values that you have to use. So now we have the z-value. Let's do the same thing with 98%. %98 confidence level, which is what in decimals? 0.98. So what do I find next? My alpha, 2%. Very good. And since right now we're dealing with only with two-tailed tests, so we have 2% divided by 2 is 1%, which is 0.01. And then what do I do with that? What do I do with this? We'll have to do 1 minus 0.01. So whatever this is goes there. So that's going to be 0.9900. So I'm looking for the z value of 0.01. That's my value. That's z over 2. So what do I go from here? I look inside the chart for 0.99, the closest I can get to it. 0.99. Here's 2 of them. Here's 0.9898 or 0.9901. Which one's closer? 9901. And it corresponds to 2.33. 3 straightforward. Here's my confidence level, my alpha, and my critical value. So if I gave you a 90% confidence interval or confidence level, what would my alpha be? It'd be 10%, which is 0.10. This is 0.90. So find the critical value. The critical value is your z alpha over 2 number. We have to look at what number we're gonna look at. So yeah, we have to do alpha over 2 first, which makes it 0.05. So our z value of alpha over 2, z value of 0.05, or 0.05 corresponds to 0.95. So what number comes closest to 0.95? The closest number to 0.95 0.95. Yeah, we could say 1.65. But isn't it close? Isn't it exactly in the middle of these two? It's 0.005 from here, 0.005 from here. So what do? We take both of these, 1.64 and 1.65, and average them. So we take 1.64 plus 1.65, which gives us 1.645. That's my z value. Make sense? So whatever your confidence level of confidence is, the difference of whatever's missing from a 1.0, that's your alpha. Divided by 2, that's the area you're looking at in your chart. The z value that corresponds to it, that's your critical value. Why do we need to know that? Is because we have all these other formulas that deal with the z values. Margin of error. The letter we use is just capital E. It's a formula. It's the margin of error tells us, given our information, how far are we from the actual number? So the formula is this. That's Q. So it's P hat and Q hat. Let me make it look nicer. What's that? E? N is lowercase, because we're only looking at the samples here. We're estimating population. So we have our critical value here, and we have our estimated standard deviation of that thing. So let's look at an example, if I can find one. Oh, here's an example. Example 2. The Sallie Mae survey. of 950 college students. %53 take online courses. Let's go ahead and find, what this one says is find the margin of error. Find the margin of error to a 95% confidence level. Find a 95% confidence interval estimate of a population proportion P and conclusion. What can we conclude about it? So what do we know so far? What are letters, what numbers do we have variables defined? Do we have N? Do we have P hat? What proportion is that? Yeah, that's 53%. What, that's the sample part. So it's 0.53. What else do we need? What's our alpha? Yeah, we're looking at confidence at 95%. So we have to find that value. We have to find, so we're using it, the confidence level at 95%. We have to convert that to the alpha, which is alpha equals 0.05. Alpha over 2 is 0.05 divided by 2 is 0.025. What do we do with this number? 1 minus 0.025 is 0.975. So that will give us our z-score, which we did that already. Where do we say it was? Was it 2 point? What else do we need to find E? To find E, we need to have the z-score. We need to have P hat, Q hat, and N. So what's the only thing we're missing? Can you give it to us? No. Well, that'll be what's left over. We had 950 people. What's 53% of 950? It's it's the opposite of it. It's since this is our success, I want to say it, but it's looking for what's not we're looking for. So our P hat would be 53% of 950, which is what? Point 0.53 times 950. $504. Actually, we don't need, these are proportional, the percentages. So we have our 1.96. We can use 0.53, and this is 0.47. We don't have to find the values here. Over n, which is 950. We can do those also. But we're looking for the proportion of it. So if we go back over here, we have 1.96 times the square root of the top is 0.53 times 0.47 divided by 950. Zero point 0.03174. Well, P hat plus Q hat has to equal 100%. So since P hat was 53%, then Q hat has to be 47%. 0.53 plus 0.47. Okay, so this is my E. Remember, what are we trying to find? We're trying to find the confidence range where the population's in the middle. So what we're looking at here is this. P hat minus E is less than our population, is P hat plus E. That's what we're looking for. That's our margin of error. Because remember, we're trying to take our sample and see, we're 95% confident that a population is going to be within this interval. So the population is 0.53 minus 0.03 less than P, 0.53 plus 0.03 for simplicity purposes. So this gives us what? 0.50, 0.56. So we're 95% confident that the population proportion will fall between these two numbers. Okay, that's the next part. Next thing we'll look at is finding the point estimate and E from a confidence interval. So now we're going to work backwards. Remember the point estimate, that's our value P. The point estimate of our P, of our population proportion, is P hat is equal to, it's a formula. It's the upper confidence interval limit plus the lower confidence interval limit. All that divided by 2. The margin of error can be calculated the upper CI minus the lower CI over 2. So for example, if I gave you the confidence interval of 58% to 81%, what is my point estimate and my margin of error? So how do you find the point estimate? Add these two up, so it's 0.58 plus 0.81 over 2. So it's 1.39 divided by 2, which will give us 0.695. And the margin of error is the upper, which is 0.81 minus 0.58 over 2. Mm, 0.23 over 2, which is 115. So that's if you are given a confidence interval to deal with, or if you calculate that first, you can find the proportion, sample proportion, and the margin of error from there. Hypothesis testing we'll worry about next time. And we'll get to chapter 8. Determine the sample size. There are two formulas. Let's first define the variables we'll be using. P is the population proportion. P hat is the sample proportion. N is the sample size. E is your margin of error. And Z alpha over 2 is the Z-score that separates the right and left tail tests. At alpha over 2. All right, so here is sample size. They have to be random samples and they have to be independent of each other. If they're dependent of each other, then we have issues because the values themselves are dependent on something else other than just red. It's just out of the blue. First one. When an estimate P hat is known, the sample size is equal to the Z-score squared, P hat, Q hat over margin of error squared. Bless you. When no estimate P hat is known. Z-score squared 0.025 and E squared. This is important. In the last example we did, we were given a P hat. We calculated the Q hat. How? One minus P hat, right? So Q hat is 1 minus P hat, right? That's easy to be done. But if we don't have P hat or Q hat, then what do? Why do we think you take 0.025 or 0.25? Because you can't take it higher than that, because if you did, you're overestimating it. You can't take it at 50% because then you're looking at 50. There's no confidence interval. So we take it at first quartile, but first 25%. Because now we're going to try to minimize our damages. Because if you don't know the P hat, then you make it as small as you can that's still valid and viable. Here's our last example. We're getting close to the end of the day. And then pretty much everything else that's it. Example 4. A 2016 survey of 4,787 randomly selected US adults showed that 79% of the respondents shop online. So if we want to conduct a new survey to determine whether the percent is changed, how many adults must be surveyed? Must to be 95% confident that the sample percentage is in error by no more than 3 percent points. I'm sorry, yeah. So do we use the first or second formula? The P hat, Q hat, or the 0.25? Are you sure? Think about it. We have 79%. What is that going to represent? That's P hat. So we'll do it both ways. With a 95% confidence level, we have alpha is what? 0.05. That makes our Z value, which we did earlier, was 1.96. So we take this divided by 2, look for 0.025 in the chart. We want error to be no more than 3 points, so we know the error is 3 percent points, which is 0.03. That's given. P hat is 79%, which is 0.79, which makes Q hat 21% or 0.21. So we have everything we need, don't we? So the sample size is equal to our Z value, which is 1.96 squared. P hat and Q hat, which is 0.79, 0.21. divided by our E squared. What does that give us? We have 1.96 squared times 0.79 times 0.21 divided by 0.03 squared. Now, here's the interesting thing. Can you get a 0.13 of a person? So always round up. So that's using our information there. Let's look what would happen if we use the 0.25 scale. So the sample would be the z-score. Put the format down real quick. So we have 1.96 squared, 0.25, 0.03 squared. One 1.96 squared times 0.25 divided by 0.03 squared. I'm sorry, 1067.11. So our N is 1068. Big change of numbers. Why is this a big change of numbers? Because this one, since we don't have the p hat is unknown, the sample proportion is unknown, we aren't too confident about it. So since we're not too sure about it, we need a bigger sample size. If we knew more information, the p hat, then we can get a smaller sample size. How much difference was there in between those two? So we have 709, 1068. $359 people. That's a lot. That's the difference of 300 people. All right. Well, that does it for that section. Yay. Then we'll finish up chapter 7 on next time, which next time we're going to look at we're not going to estimate population mean, and we won't use z-score because now we're going to look at small sample sizes. What if you can't get 900 people? What if you were in a small town, you couldn't get 900 people? So you would change it and you do a smaller one. And now we got to change the way we do the calculations. That's where the t-test comes in.